Thank you. And I'll just click back on this one.
Only if you want.
We can just stay on the motivation slide. Cool. So the applications that I mainly work on in my group in this particular project are the first two. So the first one is resource extraction. So this is extraction of natural gas from coal seams, and particularly in the idea of judging the production that a field may have to understand its feasibility. And the second one is the analyzing of the gas migration risks. So this is going to the end of the life of the wells, where you can have fractures in the cement around the well field that can allow gas to migrate to other areas that you don't want it to actually be present, particularly because a lot of the work that we do is in agricultural regions as well. So they drill lots of water wells and they don't have the type of technology they need to deal with gas kicks if they hit a particularly gassy pocket. So those are the two applications that I'm particularly interested in, but the work hopefully does have a bit broader of an application sense with a few of the other areas stated there. But the particular thing in all of these applications is the kind of key property that we want to look at is the transport and the fractures, because they're primarily a fractured media rather than a porous media. So they have these primary flow paths, which are the fractures that are present. And so to describe the goal of this research, we rendered one of our simulations to hopefully show what it might look like. So this is a fracture in a seam of coal. And there's, in this case, there's particles propagating through that system. And what we're really interested in is the effective transport properties of these particles. And so this is a nice rendering of the simulation, but all we really get from this, if we're looking for the upscaled properties, is a single point on our plot, right? So this gives us one relation of flow or transport properties based on some random, statistical representation of our rough fracture. But to feed this into a larger system, what we really need is a full curve. So we have to produce many simulations to create such a curve. But this would just give us mean properties, right? So this isn't all we want. We want to also be able to say something about the uncertainty of our predictions. So really, we want to have a distribution about this as well. This comes up with a number of issues because these distributions don't tend to have a linear relation. So the techniques that we generally use are something along the lines of gamels to take into account the nonlinearity of the distribution about the mean properties. And so the idea of the work that we're trying to do is to feed this type of relation out of high fidelity numerical simulations, and then plug the result of that into larger scale fracture generators. So that's kind of the general idea of the work that we want to do. And to put this a little bit more formally, the actual aim is to generate this statistical framework where we can build in heterogeneities in our pore space, so in the fractures, capture this in pore scale simulations, and then upscale this to the field scale while maintaining not just the mean properties, but also the variance as well. So the uncertainty that we might have in our large scale predictions. And so today I want to focus on, liquid gas flows in porous space. So I just put a little animation here to show, a phenomenon that's kind of relevant for porous media flow. And this is Haynes' jump through a system. So it's a little bit different than what I'll be talking about today, but it's just to bring your attention back to the fact that we're looking at liquid gas flows after I showed some particle simulations. So the first thing that I want to touch on is the actual generation of the geometry that we want to simulate inside of, because we want to start with we want to progress to realistic fractures. And so if we think of a fracture, the most ideal case that we could take is parallel plates. And so this is typically what's done for our larger scale simulations, because we can analytically look at this and we can judge what the permeability or the transport properties will be through these parallel fractures. And so the first thing that we're going to add to this to take a step towards some type of realistic geometry is we're going to add a roughness scale. And so we do this through a power spectrum to get the different wavelengths of roughness captured in our fracture. But then again, when you think about a fracture, they're not just going to split apart and then perfectly separate. We're also going to have a decorrelation of our surfaces as well. And so we have a decorrelation parameter in the model to generate these geometries. And then the final step is the fact that this is a random geometry. So we have to do many realizations. So that's kind of the 3 steps that we take along the way, and the couple of parameters that we use as input. And in the end, what we come up with is a 3-dimensional surface that we output in a STL, so a triangulated surface, that we can then feed into our lattice Boltzmann simulations. And so we've published the framework for generating this in a package called RFracture. And so that's what we use to incorporate into our simulations. Just for an idea of some of the physical geometries that we're looking at. So this fracture here has an aperture of 500 micrometers with a variability of roughness on the order of a mean of 20 micrometers, just to give a physical scale for what we're dealing with. Cool. And so to jump into the multi-phase part, so the lattice Boltzmann side that a lot of people will be potentially more interested in here. So we use a phase field Lattice-Boltzmann model, and we have a bit of a, I guess, a funky term or a funky method that we use for the hydrodynamics. So this is kind of seen in literature either called incompressible LBM or velocity-based or velocity pressure-based LBM. But so we actually split the Navier-Stokes equations a little bit. So we split the pressure term and the viscous term in a chain rule. We recover a part of this in the Navier-Stokes, in the LBM itself. And the others we capture in these two source terms that you see here as Fp and F mu. And what this allows us to do is it allows us to shift the error terms that are associated with density gradients out of our Lattice-Boltzmann scheme. And so these might be small parameters for your normal flows, but when you have density ratios on the order of 1,000, these terms can become present and then deteriorate the quality of your solution. The other forcing term that we add in is the Fs here. And so this is the surface tension force that we take from would otherwise be a boundary force between the phases, but because we use diffuse interface, it becomes a volumetric force over that diffuse interface. And then for the phase field component, so we use the conservative Allen-Kahn equation, which has been talked about a little bit today. And you can see one of the verification tests that we ran a while ago, and has also been in a couple other presentations this week. So there's not too much else to speak of here, except perhaps the collision operators that we use. So for the hydrodynamics, we use a weighted MRT, whereas for the conservative Allen-Kahn, we get away with just a single relaxation time. We do also have this in a central moment space as well. But typically the weighted MRT gives us quite good stability properties. And so as I was saying, we have a slightly different version of the hydrodynamic formulation, and that kind of can be seen in the moments that we have from our populations. So we have our 0th order population relating to the pressure term here, 1st order moment relating to velocity rather than momentum. And then for the Allen-Kahn equation, it's just standard stuff. So our 0th order moment is the phase parameter that tells us which phase we're in, either liquid or gas in our case. The interesting component for this is kind of the interaction of the phase field model with the walls. It's quite necessary to capture that really accurately to make sure that we're getting reasonable data out of our simulations when we're performing so many. And so there are two main ways that people do this with phase field. So they either build in a contribution of the surface energy to their free energy functional and then put that through their system. You apply some of the typical multi-phase laws around Young's Laplace and things like this to end up with the formulation that you see on the side here. Or they take a geometric argument and they use this to propagate the value of what they expect the phase to be in that solid boundary layer. And so in both of these, you're trying to predict the value of phi b in the first layer of solid nodes. And that requires some non-local information and also generally some interpolation. And so there's a number of different ad hoc approaches that people have to this in the literature. We kind of came up with a slightly different interpolation approach and a slightly different projection approach to try and minimize the number of neighbors that we have to speak to in each time iteration. Just to give an idea of the compute between these two methods, it kind of leads into the reason as to why we selected one of them. So you can see on the first side here, we have the free energy approach. So there's two plots because we do also do a staircase improvement because you need the normal direction for your solid boundary. And so if that doesn't point towards a lattice cell, then you have to do some type of staircase improvement to smooth that out. But that does come with a slight additional cost. The nice thing here is that we came up with a consistent way to do that interpolation for the staircase improvement between the two methods. So we're not adding too much extra overhead, whether we use the surface energy or the geometric. But we do see quite a deterioration in the geometric performance because we need that second order distance away, as you can see by the projection of the gradient term over here. So that increases our stencil, increases our communication, reduces our performance on the GPU. So this is kind of an idea of how we do this in the initialization stage. So what we can do is if we have a completely random field where we don't know the normal values, we can assign zeros and ones. We can do this kind of gradient calculation and come up with some approximation of the normal. People generally do other things on top of this. They may smooth this. The nice thing about the fracture cases that we have is because we're generating STL geometries, we actually have the normal directions as well, and we can prescribe those in the simulations. But in a more general case, this is the approach that we take. And so once we have this, the normal, as you can see by the image here, is very unlikely to be pointing at the direct neighbor. And so when we're trying to grab the value of phi or grad phi in that neighbor, we're not able to do it. And so we use, in our case, a trilinear interpolation because, again, we're trying to reduce the amount of communication that we have so that we still have reasonable parallel performance. So we're making the most of the bandwidth of the GPU to actually perform our memory-bound algorithm as efficiently as we can. And so we do have some details for this that will hopefully be in a publication soon that I'll be able to point you towards if you're particularly interested. Cool, but that kind of wraps up some of the stuff on the methodology. As I was showing some stuff on the methodology, I didn't want to jump into the fracture flow results without showing some type of verification. And so we did do a number of verifications for this. So one you saw in a GIF in an earlier slide, which had a droplet colliding with a sphere. The other one is droplets spreading on a sphere that a couple other presentations have had this week. And the one that I'll show here is just known as the Washburn law. So it describes the imbibition of the fluid into a capillary tube based on the pressures that we have in the system. And so you can see the image of the tube up here on the side. And the thing that I want to highlight here is that we're specifically trying to capture these scenarios with relatively coarse grids, because often if we're doing porous media flows, it's okay for the fracture flows, but for porous media in general, where we have a CT scan, we're not always going to have the best resolution through our throats. So we did test this, for example, a resolution with 5 lattice cells across our radius and 10 lattice cells across the radius. And in both cases, they perform reasonably nicely. But the thing that I want to emphasize here is that the two implementations do perform differently. So based on which implementation you use, you do get slightly different performance of the dynamic motion of your interface through the system. And we've seen this in more complex cases as well. And so it is quite sensitive on which approach you actually take, which is a bit of a not a great aspect, I suppose. Some of the other parameters that we have for the simulation can be seen on the side. So we do achieve high density ratios quite comfortably with this model, which is a nice aspect in a comparison to a number of other multi-phase lattice Boltzmann models. Cool. And so with that, I now want to jump into, I guess, a bit more of the meat of the results. And so this is jumping back to the fracture cases and the parameter that we really have of interest for the liquid gas flows. So for the liquid gas flows, the way this enters into our relation on a larger scale is into the Darcy equation. And as you can see here, there's this Kr comma alpha term. And so this is our relative permeability. So it's a weighting on the absolute permeability, which can be taken as almost a material parameter of how a fluid transports through a porous media. In this case, our porous media is a fracture, but we can still apply the same analogy to this case. And so you can read some of the stuff on the left-hand side, but I really want to draw your attention to the images on the right. So the relative permeability curves look like this image at the top here. I'll just use the mouse, where you have the lines coming down from the top left to the bottom right is the relative permeability of the liquid phases, where the lines going from the bottom left to the top right is the relative permeability of the gas phases as the saturation of the liquid phase increases. And so these are the types of curves that we want to get at the end so that we can feed them into our larger scale simulation plots and kind of fill the loop that we have here on the bottom right of what we're trying to do in this body of work. So for the fracture cases themselves, they're not super large. So the domain that we have is 288 by 288 by 32. And the way that we generate the fractures is in a normalized sense. So if you look at the second, oops, sorry, looking at the wrong screen myself. If you look at the second line here, you can see that we have a mean aperture of 1 with a 20% roughness ratio on average through the system. And then we scale that into our domain. So the mean aperture for these is actually about 16. And the 32 cells is to cater for the fluctuations in the rough surface. And so we have that. And then for the next component that we need to worry about is the initialization. And so for the initialization, we also do this with a random field. But there's some subtleties here that have to be thought of when you're trying to apply this to many realizations. So the aperture field of your fracture is changing with each realization. And so if you just applied the same cutoff values in your random field to generate a certain saturation, you get slightly different values for each realization. And so into our workflow, what we do is we actually have a bisection method that looks at the fracture field, looks at the random field, and then tries to do a bisection method to come up with a value that will give us the exact saturation that we want. And so that's done as kind of a pre-initialization stage of the lattice Boltzmann setup itself. So the other interesting component here is that this is done in a fully periodic cell at the moment. And so this does create us some issues in terms of the length of simulations that we have to run. But there are some interesting things around the body forces that you can apply to make sure you have a constant pressure differential across the system. So that can be seen here by applying both an acceleration and a buoyancy term. And so I'll jump through a little bit now because I think I'm getting close to my 15 minutes. And just show some of the raw results and talk about the methodology. So what we did for our initial test setup was to do simulations at every 0.1 of saturation between 0 and 1. And we did 10 realizations of each of these. And so we ran this on one of the supercomputing centers that we have in Australia, because the simulations themselves take quite a while because you come up with these pseudo steady state results. And so the raw data here is on the right to show the fluctuation or the differences that you can see with the different fracture realizations. And so you can really see that evidently in some of the ones around for the saturations in the middle zone, where you have areas of no flow compared to areas of flow, because they've reached different stagnation points inside of the geometry itself. And so that's the type of variability that we want to capture in these types of analyses. So just in the idea of time, I'll jump to the smooth looking plots of the actual simulation field. So this is the same setup, but just 3 different realizations. And the thing that you can tell here is that the end result of the topology of the interface varies quite substantially between these cases. And so that's the type of variability that we're now trying to capture in the model to then propagate into the macro scale system. And as I said, we do this through the relative permeability curves. So we can take the mean properties, we can take the variance, and we can also look at the extremity values, which tend to be quite interesting because then you see the points where you have real kind of behavioral change positions, where you have sections of no flow for some realizations of fracture roughness, whereas quite substantial flow for other realizations. And so that kind of highlights some of the things that you miss if you don't do many realizations in random types of geometries. Cool, so with that, I'd like to thank you for your attention. Here's some of the references in terms of the models that we use in the Lattice-Boltzmann side, and feel free to ask any questions that you might have.
Do you observe that for the same realization, but with different initialization, you converge to a different?
Yeah, so we're actually doing a bunch of simulations of that at the moment, and the initial ones show that we do get slightly different behavior. We haven't seen any with the same realizations and different initializations that will cause quite the like no flow, for example, in one and flow in another. But we do still see slight variations in the mean properties. So yeah, it's a nice question because it is like another random aspect that we're adding into the model. And so yeah, we do see a little bit of variability.
Okay, quick question. Yeah. Slide 7, not 2 videos.
Yeah, I'll jump back.
No, the difference between the left and the right video?
Back on slide 7. The simulation here. Sorry, I should have said, I'll try and get the video to play again. So these are actually the same model. They're just different density ratio flows. So the density ratio on the first one is around a 3, which is the one that a lot of people start with. And this one here, just to show the model can capture a density ratio of thousands of liquid gas properties, even with quite complex interface topologies. Yeah.
Very much.
Thank you.
It's supposed to be
Okay.
So instead there is the implementation of the session is some power. And it's relevant to high performance reactive transport model for cement based on interfaces.
Thanks. So welcome to my presentation about high-performance reactive post-scale model for cement claystone interface simulations. So to dive in directly into the cement claystone interface, it is mostly important for the radioactive waste disposal. For example, Switzerland plans to embed the light and intermediate level waste into concrete and mortar, both different forms of cement, surrounded by the opalinous claystone as the host rock. So to produce cement, calcium carbonates are heated to form calcium oxide, which is then hydrated with water to produce cement, which mostly consists of portlandite and CSH. Portlandite is calcium hydroxide, and CSH is calcium silicate hydrate. It is CSH is a semi-crystalline phase consisting of calcium oxide, silica, and water in a sheet-like structure. can consist of different ratios of the composition, which can be constituted as a solid solution of 4 different end members called tobermorite D, H, and jenite DH. An important characteristic of CSH is its shield porosity with values up to 30%, depending on the solid solution state. This is important because it still allows the migration of cations and anions through the shield porosity, which influence the evolution of the cement claystone interface and also allows the migration of radionuclides, which impacts the safety assessment of the underground repository for the radioactive waste. So I use reactive pore scale model to investigate the claystone side of the cement claystone interface. So here you see an example of a claystone and the solids are dark gray and the pore space is colored. There is diffusion through the geometry due to fixed solid concentrations at the boundaries, and the mixing of both of the solids then allows the precipitation. So the diffusion is simulated with the Lattice-Boltzmann method, and the precipitation is calculated by a geochemical solver, which is coupled with the Lattice-Boltzmann method. Here it's the precipitation of CSH. So a problem of this method is that it's quite slow. So this simulation would take 300 years to complete, which is a bit too long. So the goal of my project is to generate an algorithmic advancement to accelerate such reactive pore scale models and apply it on the cement claystone interface. I do that by first replacing the geochemical solver with a neural network, and then in a second step with the adaptive time stepping algorithm. So the cement pore water has a high pH and high calcium concentrations, while the claystone site has a pore water with neutral pH and an inventory of silica. This chemical contrast leads to the flux of aqueous silica into the cement, where portlandite starts to partly dissolve, and the resulting aqueous calcium hydroxide diffuse into the claystone. There, the mixing of both solutes allows the precipitation of CSH. This will eventually clog the whole interface and generate a low porosity zone. So this geometry resembles the pore space of a claystone, which is resolved into equally sized voxels. They have either the state of fluid, here blue or green, depending on the solution, or brown if they already contain CSH precipitates, or they can have the state of solid, here dark gray for the inert clay minerals, or black if the pore space voxels are completely filled with CSH. There is a flux of aqueous calcium hydroxide from the left and aqueous silica from the right side into the geometry with solution concentrations in a realistic way. The simulation starts with an initialization and then sequentially computes with the operator splitting approach the diffusion with the Lattice-Boltzmann method, and then the chemical reactions, here the precipitation of CSH on every fluid voxel. The locally calculated precipitation of the 4 CSH end members adds up as volume percentage in every voxel. And then when a fluid voxel reaches 100% of precipitates, it turns into a solid voxel. So now to the first acceleration technique. So usually the Lattice-Boltzmann method is coupled with a geochemical solver. It goes over all voxels or fluid voxels at every time step to calculate the precipitation, which is quite time consuming because the geochemical solver is a computationally demanding algorithm. So it is an established method to replace it with a neural network that is trained on the specific chemical system. For that, I generated datasets with the geochemical solver GEMS, with data points in the expected concentration range that will occur during the reactive transport model. Then I generated an optimal architecture for the neural network. So this one here takes the two solid concentrations as an input and gives the precipitation of the four CSH end members as an output. Then it is trained and tested on the generated datasets and received a mean squared error of around 10⁻⁴ in this case. After integrating it into the reactive transport model, it accelerated the whole simulation by 100 times. So the previously shown simulation would now take only 3 years to complete, which is still too much. So we need more acceleration. So that's where the adaptive time-stepping algorithm comes. So this reactive transport model consists of diffusion, precipitation, and solid growth. In this video here, you see the concentration profile in 1 dimensions, and there's a fixed height concentration on the left and the fixed low concentration on the right side. This chemical gradient is balanced by diffusion through a solute flux, which starts to increase and then reaches a steady state, here in red, of constant solute flux. This constant solute flux then also leads to constant precipitation rate on every voxel. It is a quasi-steady state because the solid growth will still progress, but it progresses with constant values due to the constant precipitation rate. It is a temporal quasi-steady state because the solute flux will change again when the pore space alters by solidified voxels. Now this can be used to accelerate the simulation by skipping the simulation of diffusion and precipitation at every temporal quasi-steady state and apply an increased adapted time step only on the solid growth, which progresses constantly anyways, until enough voxels are solidified to loosen the system from the temporal quasi-steady state. So for that, I programmed the adaptive time-stepping algorithm within the reactive transport model framework of the Lattice-Boltzmann method. The temporal quasi-steady states are detected by monitoring the average solute flux and precipitation rate at every time step, and when their corresponding relative errors over the last 50 time steps lay beneath the specific steady state threshold, an acceleration step begins. For an acceleration step, the simulation of diffusion and precipitation stops, and it is calculated. It is determined which voxel would theoretically solidify next, and then the required number of time steps to solidify this voxel is applied on the solid growth of every voxel according to their current precipitation rates. So, yeah, and if it's also checked if other voxels would solidify in a close time span, and if so, then the increased adaptive time step is slightly increased more, which is important for large geometries consisting of millions or billions of voxels to prevent the necessity of having an enormous amount of acceleration steps. Because without this part, it would only solidify 1 voxel per acceleration step, which can lead to millions of acceleration steps required to complete the simulation. So the adaptive time-stepping algorithm is benchmarked on this geometry with reactive transport models that all have the neural network integrated, and the simulations are stopped when the pore space is clogged by CSH precipitates. The shield porosity of CSH is not considered for the reactive transport model. Several simulations are performed with different steady state thresholds, which you can see here in different colors, and compared to a simulation without the adaptive time-stepping algorithm, here in red. The comparison is done with the trajectory of the effective diffusivity. It is a value that compares the diffusivity of the geometry, dE, with the diffusivity in plain water, d0. It is calculated separately from the reactive transport model by extracting snapshots at different times during the reactive transport model, and then simulating the diffusion at every snapshot until steady state is reached, and then the solute flux at steady state can be used to calculate the effective diffusivity. Important to mention is that for the simulation of diffusion, the shield porosity of CSH is taken into account. So the CSH precipitates will lead to an evolution of the microstructure, which can also steadily reduce the effective diffusivity. And because the shield porosity is considered, it will not reach zero even after total clogging. So you can see that the simulations with steady state thresholds of 10 power minus 4 and 5 power minus 5 show a close resemblance to the red trajectory. This can also be quantitatively compared with the time of clogging, here the circles at the end. And both simulations reach relative errors below 2%. Higher steady state thresholds lead to higher errors because they determine the temporal quasi-steady states early and obviously too early. But it also leads to higher accelerations. So, however, the simulations with good accuracy still have an acceleration of 90 times. So it took 1 hour to finish the simulation with a threshold of 10 power minus 4 instead of 1 week without the adaptive time-stepping algorithm. Now, the adaptive time-stepping algorithm is also tested on a larger geometry with lower precipitation rates. A simulation without the adaptive time-stepping algorithm is not performed due to time reasons because it would take 3 years. You can see that the steady state thresholds of 10 power minus 4 and 5 power minus 5 show a close resemblance, which indicates close convergence towards a real value. Yeah, now you can see it better. Yeah. Now the lower precipitation rates lead to the fact that the simulation spends more time during temporal quasi-steady states, and to skip them then also leads to higher accelerations. So here, up to 9,000 for the simulation with a steady state threshold of 10 power minus 4. So instead of 3 years, it now took only 3 hours to complete this simulation. Now, the significant acceleration allows us to conduct several simulations to test different chemical conditions to increase the time span and or the geometry size. This pore scale model also gives insights into values of all relevant parameters at every location of the pore space and at every time. An example are the CSH precipitates, which you already saw before. But we also know the ratio of the CSH end members from the CSH, which can be used to calculate the calcium to silica ratio of the CSH, which is important because it influences the migration of, for example, radionuclides in the repository by several magnitudes, because it influenced the shield porosity. Now, to conclude, I trained and tested a neural network for the CSH precipitation in a claystone and programmed and tested the novel adaptive time-stepping algorithm, which has a good accuracy with errors below 2% and accelerations by 90 to 9,000 times, depending on the chemical conditions. The neural network accelerated the simulation by 100 times. So the total acceleration of the whole setup is by 9,000 to 900,000 times. This reactive transport model also gives us insights into local values of relevance, complementary to experiments or macroscopic models. Here you can see some references, and with this, I'm finished. Mhm. Ah, yeah, the time is scaled. So here to the simulation of like at the clocking, yeah. Mhm.
What's the real time in the minutes, seconds? Yeah.
Several hours. And I scaled it because then you can see the comparison better to the simulation where we compare the other simulations.
Faster than you would expect in the country. Very small scale and very high gradients. Like, people made experience with this small scale phenomenon.
I think the curvature of the various crystals also will impact the diffusion rates. And
Mhm.
do you think that would be possible to include into like the new network to also have the heuristic and whatnot that would use that?
No, but if there is data available for that, it is possible to include it into the neural network. Yeah. But I don't know if it's available for CSH. Also, it is a semi-crystalline phase, so it's the structure is not really clear and possible to investigate by common techniques.
Any other question? Okay, so let's thank the speaker. Patient inside Ricardo and Karin, and then
Good afternoon, everyone. My name is Ricardo Leite Martins Bazarin. I am a postdoctorate in the Scientific Computing Laboratory at the Federal University of Santa Catarina in Brazil. And I'm here to present my work, Lattice Boltzmann Method System for the Buccal Leverett Equation. And it has collaborators. One of them is the Professor Diogo Nardari Siebert, and the other one is the Professor Luiz Orlando Emerick dos Santos. The Buccal-Leverett equation is an equation proposed by Buccal and Leverett in 1942, and it aims to describe a biphasic mass balance in a porous continuous porous media. The porous continuous porous media is a porous media where we can't distinguish the interface between the fluids and the interface between the solids. And we represent it only with parameters as saturation, porosity, permeability, and average velocities. In the oil industry, the Buccal-Leverett equation has a lot of applications, but the main one is to simulate reservoir scales, simulate the fluid displacement in reservoir scales. And the black oil model, it's the main one, and it's considered like an extension of the Buccal-Leverett equation. The Buccal-Leverett equation characterized by three different main formulations. To explain a little bit about them, I will use a benchmark case that is represented by a linear reservoir where we have a porous media saturated with oil, and we will inject water by its side. And when I will approach this problem with a convective formulation, the simplest one, we have a derivative term of the saturation and other two convective terms. These two convective terms create a monotonic solution where, dependent of the point during this case, we'll see the increase of the saturation independent of the point, and it will also characterize a sharp front displacement that will create the displacement between both fluids. The second formulation is the convective diffusive formulation with static capillary pressure. This term of capillary pressure will introduce the diffusive effects, and for the same problem, we will notice now a diffusive effect in the sharp front simulation. And the last one is the convective diffusive formulation, but now with dynamic capillary pressure. And this term changes a lot the phenomena in this case, because it will introduce non-monotonic solutions where we can have a overshot in a region during the displacement. So all those equations are nonlinear equations, and this nonlinearity appears when we substitute the permeabilities using a correlation. In this case, is the Corey correlation using a quadratic exponential term, where this exponential term could vary in order of the relative permeability you want to represent. But in this case, we use a quadratic representation where the relative permeabilities will be a function of the saturation, the square of the saturation. So we substitute this term on it, and we have the equations now in this formulation. So I did a literature review for Lattice-Boltzmann methods that represent Buckley-Leverett equation, and I just found 4 articles. In all those, just approach the convective diffusive formulation with static capillary pressure. So in this way, the proposal of this investigation is evaluate the Lattice-Boltzmann system for convective formulations of the Buckley-Leverett equation, extend the literature analysis for the convective diffusive formulation with static capillary pressure, and also develop a Lattice-Boltzmann approach for convective diffusive formulations with dynamic capillary pressure, and also observe and numerically validate the saturation profiles with non-monotonic behaviors. So here we start with the simplest formulation, the convective equation. So I have here the equation that I want to represent, and for it, for this I have I use the equilibrium function just with the 0 order moment and the 1st order moment, and for this case I can represent the problem using the Lattice-Boltzmann equation in an equilibrium state. So performing Chapman-Skog analysis, I will need just the Newton terms of 1st order to recover my desired equation. Here is the problem. So in this case, I consider the same linear reservoir, and I consider a average velocity equal to 1 and a viscosity ratio equal to 1. Here is the Lattice-Boltzmann equation, and I will scale the velocity by delta t divided by delta x. So simulating this problem, I plot the saturation profiles for 2 different times, and we can see that when we double the mesh, we're finding the lattice-Boltzmann grid, the results converge for the analytical solution of the problem. I also perform a convergence rate. In the first case, I fixed the velocity and I doubled the grid. And for this case, the slope was smaller than the first order. I obtained at 0.8. And in the second case, I fixed the delta t and doubled the mesh. In this case, the convergence rate was better, almost the double. I reached 1.5 in the convergence rate. Now the second formulation, the convective diffusive equation. I have the equation that I want to represent here. In this case, the equilibrium distribution function needs a second order term to recover the macroscopic equation. And in this case, the second order equilibrium moment is the lambda tensor that will be equal to a gamma tensor plus the static capillary pressure term. The gamma tensor is a correction term proposed by Shi and Gu, and also used by Shai and Shi. And it works well to recover the desired macroscopic equations. And in this case, the lattice-Boltzmann equation will be necessary. I represent the non-equilibrium effects on it. So I have a collision model. In this case, I use the BGK collision model, BGK collision model. Here I perform a Schaffmann-Skog analysis of the equation. Now I have to extend to the second order terms. I have the first order and second. I will sum for the zero order moment, and I summing the Newton orders. I recover the desired equation, but now I have a constitutive term that is lambda, and it scale delta t by delta x squared. And this term will control the intensity of the diffusivity in the process. Here I have one case analyzed. This case is based on the work of Kuganov and Tadmor. I consider a average velocity equal to 1, the viscosity ratio equal to 1, and the diffusive term is equal to 0.01. I have an initial configuration of the saturation. And I start the simulation up to the time 0.2, and I double the mesh, and we can see that the saturation profile converges well to the results presented by Kuganov and Tadmor. And I also did a convergence rate. In the first one, the convective convergence rate. I fixed the velocity and double the mesh. I use, in this case, that's not analytical, a reference mesh of 12,800 points. And I have a average slope of 1.2, and also a diffusive convergence rate where I fixed the diffusive term and double the mesh using as a reference a mesh of 3,200 points. And I have a slope a little bit similar of in the average of 1.2. Now, the last most complex one, the convective diffusive equation with the dynamic capillary pressure term. In this case, I will have 2 constitutive terms and 1 third order derivative term. And to handle this, I used the same equilibrium function of the last formulation. And now I have to use in the lattice-Boltzmann equation an MRT collision model. And in this MRT collision model, I will have 3 relaxation times, but the tau 0 doesn't matter. The modeling satisfies the saturation balance, so doesn't matter its value. And the other 2 relaxation times, tau 1 and tau 2, will be responsible to represent the 2 constitutive terms. Here I perform a Chapman-Scott analysis for this problem. Now that I have to recover a third order term derivative, I have to extend my analysis to the third order of Knudsen terms. It's a very tough calculation, but it's here a resumed part of it. And here I sum them for the zero order moment. I recover the terms, and I recover the constitutive terms as a for the diffuse terms in the same way of the last formulation. It depends only of tau 1, but the second constitutive term, it's a function of both relaxation times, tau 1 and tau 2. And I recovered this term in this formulation, and it has a specific aspect that's not so good. When I scale the problem, could happen that I have here plot a specific region of a range variation for both constitutive terms, and depending of this range, I can have a negative relaxation time, and this doesn't make sense. The relaxation time can't be a negative time. And of course, in this case, the simulation will become unstable. So I have to avoid this and also have positive terms. But the second constitutive term is just dependent of the refine of the mesh of delta x squared. So I have in this way a limit of for refining my mesh, and that is a big problem. But as we will see, I applied this model for this specific case. I have an average velocity equal to 1, viscosity ratio equal to 2. The diffuse term is 0.2001, and the epsilon term that controls the intensity of the second constitutive term is equal to 3.5. And I simulate it double the mesh from 200 to 800 and compare to the results of Cow and collaborators from 2014. And I recover his results very well. But my I still comparing the saturation profiles. I just put here a comparative the effect of the dynamic capillary pressure for that I simulate with the static capillary pressure to compare the effects and demonstrate that the model is correcting recover the effects of the dynamic capillary. In the convergence rate, I compare double the mesh for a convective case fixing the velocity, and I use as reference a mesh of 800. Because if I increase the mesh for 1,600, for example, will happen that case that tau 2 become negative, and the simulation becomes stable. I did the same case for the diffusive convergence rate, fixing the diffusive term. And in this case, when I take into account all the points, I will have a slope approximate of 1.1 or 1.2 maybe. But we can see that the convergence rate increased a little bit when I take into account point by point. But it's not so relevant when I have a limit of mesh to perform it. And that's it. My conclusions were that the convective and convective diffuse formulation were well represented, but all the formulations present a convergence rate more closer to the first order. That's not so good. And despite being functional, the convective diffuse formulation with dynamic capillary pressure still needs to be improved. It had a little bit problem, but worked. The next steps of my work, and that's the motivation that I did this study, that we want to develop a multi-phase, multi-scale porous media for LBM. And the idea here is coupling the porous scale with the continuous porous scale. I put here a example similar to the case that I present. I have a porous scale, here porous continuous scale, and a porous scale. I represent the power scale with the color gradient model. Here I have the Buckle-Leverett equation. And when I inject the fluid, I can restart the GIF. But here I have a power scale displacement with interface. But when it reach the power scale, the coloring step of the color gradient model is removed, and I have a diffusive effect where I have both fluids flowing in the same direction, and in the outlet point, I have a specific aspect that I have both fluids coming out from the porous continuous region at the same time. And in this way, I will have a segregation effect that will separate the phases in layers. In this case, happen this oscillation in the saturation profile. And for completing this multi-scale porous media for LBM, we have to add a momentum balance equation, but this is not so difficult, I think, because in my model, the mass balance is not, the mass is not coupled with the pressure. And in this case, the momentum quantity will have our own density represent the pressure. So the power scale and the mass balance scale just has to adapt to the momentum balance equation. And that's it. Thank you for your attention. Bye.
Covers this convergence of deterioration in the two first stages.
In the two first, convective and convective diffusive with yeah, it's a nonlinear problem, and I don't have a basis on the literature for this kind of problem, but could be a lot of things. Could be maybe boundary conditions or a better improved collision model. It's difficult to say, I think, but yeah. Yes, yes. The first one, I don't need a collision model because I can recover the exact equation with just a equilibrium state. So if you put a non-equilibrium effect, you will introduce errors. And in the second one, I need the non-equilibrium effects. And in that case, I use the BGK, but I could try to use MRT and find a combination of relaxation times to improve it, maybe. But I don't know. I have to try to say if it's that. Yeah, in the first two problems were very similar problems. I have a constant saturation in one side and a new gradient saturation in another side. And this new gradient saturation is on interpolation, yeah, of course, interpolation between the 2 points. This is not good. This could be one of the problems. Improve a kind of a specific kind of improved no gradient, but I have to try also. And the saturation, it's very simple. I just have to, I have 3 velocities, one-dimensional problem. I didn't say that. I use the D1Q3, and 2 velocities I know. The other one is just to adjust the value that I want for saturation. So, yeah.
Okay, is there any other quick questions? No, that's, thank you again.
Okay.
The next presentation is on pain, and it's relevant to physical pain of carbonate precipitation experiment. What is the role of full-scale modeling and mass level?
Yeah. Okay. So good afternoon. So I'm going to talk about some recent progress of my PhD project, which is how we use numeric-based modeling tool to develop the digital twins to explain the complex physical-chemical process of calcium carbonate precipitation in porous media. So, okay, let's start with the motivations. As we all know, calcium carbonate is ubiquitous in both engineering and science, and is by far the most studied solid phase. So it's quite important to understand its complex physical-chemical behavior because it may have an influence on several industry processes and also engineering application, including enhanced oil recovery, carbon sequestration, geological disposal, and also, of course, your thermal energy extractions. So what's challenging in studying calcium carbonate? So here is a really classic counter diffusion experiment. So inside the capillary, we can see then different forms of calcium carbonate precipitated in the different location of the capillary. So this is a really interesting phenomena as the formation of the different polymorphisms of calcium carbonate is jointly influenced by several factors, such as local pH condition, the temperature, the concentration of the ions, and moreover, the precipitation mechanism is a really complicated process as it may involve multiple steps such as ion migration, nucleation, growth, dissolution, recrystallization, and of course their own chemical interactions in the solutions. So for experimentalists, it is quite challenging for them to predict the dynamic precipitation process, and it's really hard for them to obtain such a chemical information during experiments. So that's why we need a numeric-based predictive model that to help us to complement such experiments. So let's lead to the concept of our digital twin. So what is digital twin? Digital twin is actually a modeling-based tool of increased realism. So it has two important parts. First is experiments, and the second is modeling. So once it's developed, it can help us to do model validation. It can help us to analyze the structure and dynamic of such a precipitation process. Of course, it can further help us to do predictions, parameterization of experiments, and can help us to understand the relevant process that happens in experiments. So what's the advantage? So we serve this as an evolution of previous numeric simulations. So we can obtain full chemistry information during the simulations. And we are performing 3D high resolution rate transport simulation, which is maybe more accurate than the previous 1D or 2D results. And the most important part is the computational time is ultra-fast in real time. So even heavy computational task, we can be finished within several minutes or even seconds to complete. So let's go to our first component. So which is the counter diffusion experiment. So this experimental setup consists of a 300 micrometer wide capillary, so filled in with silica gel as porous media and connected by opposite sides by two reservoirs. So one is containing calcium chloride and the other one is containing sodium carbonate. So silica gel was chosen here as porous media because it's optical transparency, so which allowed us to continuous monitoring. So the relevant process was monitored in real time by optical microscopy at the select times ranging from a few hours to several months and up to 1 to 2 years by using the XRD, XRF mapping technique at the Swiss light source. So this part is done by my colleague, Dr. Daniel Gorniman and Dr. Ashes at Swiss light source. And here what I show you is some one of the experimental observations, so in which we can clearly observe that the different polymorphisms of calcium carbonate are identified. So we will observe calcite nucleation and growth at the low pH site, and we will observe some batterite nucleation and growth, and followed by the recrystallization to calcite. And we even observe such sudden formation of the nanoamorphous calcium carbonate precipitation in the middle. So obviously, it's a really complicated process that for experimentalists, they may only have limited information to explain. So that's why we need our modeling to help them. So come to the numeric modeling tools. So the first model I used, of course, is a Lady Sportsman model. So we will use multi-component Lady Sportsman model to simulate the counter diffusion process of the sodium carbonate and the calcium chloride. And we also implemented the volume pixel method to update the solid phase and to simulate the dissolution precipitation of different calcium carbonate polymorphics. So the second tool we used is the James software. So this is a thermodynamic software package that uses Gibbs energy minimization for analyzing complex aqueous geochemical systems. So here, Lady Sportsman method performs the physics simulation, and all the chemistry information will be obtained by James. And the third tool, we will apply machine learning. So machine learning will be used in here to significantly accelerate both the physics simulation and also the chemistry calculations. And we're also using some optimization method, which can help us to find the minimal difference between the experimental results and the numeric predictions. So just give you a first example of how we develop a digital twin for diffusion experiments. So since the transparency property of the silica gel. So before we started the real counter diffusion experiments, it's quite important for us to know the diffusion coefficient of such porous structures. So the idea of such a digital twin for diffusion experiments is to help us to do the inverse modeling to fit the experimental results to find the best fit diffusion coefficient of such a systems. So for experimental part, we inject the bromide from left to right as a tracer, and by using the same experimental setup. And from the XRF measurement, we could obtain the concentration profile along the capillary directions at the different time steps. So for the numeric part, first we need to generate a 3D geometry that precisely replicates the experimental setup. So this geometry has a resolution of 0.05 millimeters. And also the reservoirs are replaced with the constant inlet and outlet boundary conditions. Here we treated the porous media as a homogeneous porous media. And with this geometry, we then generate some training data set for our machine learning. So the whole training data set consists of 13 cases of the latest Boltzmann simulations with 13 different diffusion coefficients, so ranging from 5.5, 10 to the minus 10, to 3.55, 10 to the minus 9. So we output the concentration profile along the capillary directions at a 2-hour interval of a total of 150 hours. We then train the machine learning model with this dataset. So what we are using here is a simple feed-forward neural network. So this is a specific type of neural network that the information only flows in one direction, so from left to right. So we have 3 parameters as input, which is the diffusion coefficient, the position, and the time. And one variable as output is which is the corresponding concentrations. So the well-trained neural network will have the ability to fast and accurate predict the concentration profile based on specific input. So with such a pre-trained neural network, we then can couple it with the optimization method to help us to find the best fit diffusion coefficient. So the target function for the minimization is actually the normalized mean square error between the experimental diffusion profile and the numerical simulations. It can be seen in here, we only need 9 iterations to achieve this optimization process. And here we compare the experimental diffusion profile with the numeric predictions with the optimized diffusion coefficient shows relevant good agreement. And here, based on the numeric procedure, what I show in the red box, I just give you a really quick summary of the digital twin for diffusion experiments. So the optimization task with this developed digital twin to help us to find the best fit diffusion coefficient of the system is really fast. It just takes seconds to complete. And if we directly couple the LB method with the optimization methods without the usage of machine learning, so it may take days or even months to complete. And the total time cost for developing such a digital twin, so including dataset generation and the training process and the optimization process, is less than 15 hours to complete, so which is far shorter than the 130 hours to perform one actual experiment. And the developed digital twin so supports fast and repeatable simulation for similar experimental design without the need for retraining. So next, I will show you. I will give a quick show you about the diffuse digital twin for calcium carbonate experiments. So this work is currently ongoing. So I will just quick show the workflow. So first, we will use the multi-component Boltzmann model to do the solute transport of the chemical species. So in our case, which is the counter diffusion of the sodium carbonate and the calcium chloride. We then can couple the chemistry neural network with the LB solvers to do the thermodynamic equilibrium and geochemical speciations. So in here, the reason why we do not use the traditional chemistry solvers because it can only update 1,000 work cells per second. But for our transport solvers, we can easily update it more than 10 million work cells per second. So if we're directly coupling these two together, the chemistry part will consume 99.9% of the computational time, which is really impossible for us to perform one actual 3D simulations. So how we train such a chemistry neural network, we still need the traditional chemistry solver to pre-calculate the samples that spawns of the possible solutions to generate the training data set. So in our simple systems, we have two species as input, which is the concentration of our primary species. And we have three variable as output, which is the activity of calcium and the carbonate, and also the relevant pH value, which will be used to later simulation of the dissolution and precipitation process. And in order to consider the nucleation into our model, of course, we are applying the classical nucleation theory, and which the nucleation rate is a function of saturation index and the concentration of calcium and carbonate, and the induction time is related to nucleation rate and the local volume of the pool. So for the nucleation of different polymorphisms of calcium carbonate, we constrain this by using the empirical threshold of the pH as saturation index to achieve this. And further, we also want to describe the formation of the non-amorphous calcium carbonate in our model, so we will apply non-classical nucleation theory. And also we need to further incorporate the dissolution precipitation models, which we will use general rate law equation to calculate the reaction rate. So from this loop, we can finish the design of our digital twin for calcium carbonate experiments. So actually ideally for certain experimental results, what I show in here, so our modeling cannot just capture the physical behavior of the different polymorphisms of calcium carbonate, but also provide valuable chemistry information. So it is foreseen that a large number of virtual experiments will be conducted in helping of designing new experimental setups. So in here, I give a quick summary of our work. So what we have done, we have already developed a digital twin for diffusion experiments, which can help us to find the best fit diffusion coefficient of the system. And this kind of framework is quite straightforward to implement for high-dimensional problems. And what we are ongoing, we already implemented the chemistry neural network and the classical nucleation theory into our models. And the comparison between the first nucleation point in experiments and the modeling is currently ongoing. And of course, future work, we will introduce a non-classical nucleation theory, and we will couple our simple dissolution and precipitation model with full chemistry informations. And that's all I wanted to talk today. Thank you.
So this chemistry neural network
Yes.
So in general, at the maximum, on how many number of species have you tried? Like, could you do 5 species?
Yeah, it's straightforward because here we only have 2 input and 3 output. That's because this is all we need for the later simulations. You can like increase the number of species that you are interesting. You can output like more information you want. Of course, this is no problem.
Max, how many?
At least 8. We could try. Yeah, 6 or 6. Yeah. Yes.
And at the output, how do we say it? It satisfies the conservation laws currently, like the rates,
Mhm.
net rates are.
You mean the mass conservations? It depends how you train the neural network. So the performance of your neural network is based on the mean square errors. So as long as you have low mean square errors, so it shouldn't be any problem. Yeah.
Any other question?
Touch small diameters of the test tube, the growth of crystals when it is totally dependent on the orientation of crystallographic lattice.
You mean the orientation of the crystal growth?
Yeah.
Yes, that's cool. We didn't implemented some complex model like freeze field or some other techniques. We are treating this crystal growth using the traditional way. So currently, we do not have a function to describe the orientation of the crystal, but our reaction rate already shows a really good algorithm with the experimental results. Yeah, it's based on the local condition because the reaction rate is based on the local saturation index. So for each work cell, the saturation index is different. So that's some work cell maybe grow faster, some other maybe not. Yeah.
So there's no other question. Yeah, first of all, thank you so much for managing the time slot. So I try to present on behalf of my colleague. So in this talk, we talked about multi-component, multi-scale simulation model. So a few years ago, we introduced a multi-scale and multi-component fluid model. So for example, if this image are given and then supposed to simulate the simulation flow, to perform some simulation flow from our side to other side, then because this structure, including the small structure and also the large structures, and if we try to resolve all of them with fine resolution, it's very, very expensive. It's almost prohibited. So our approach is to use the reasonable resolution, but at that time, some image become like a gray scale color here. So that is in the middle of a solid and fluid. So for that region, we model the fluid force that's almost coming from viscous force and then capillary force from small structures. So specifically, we perform pre-simulation with pick the characteristic small rock structures, and the simulation simulates with very fine resolution. Then we get the absolute permeability, capillary pressure, relative permeability at that characteristic system. Then we use this physical quantity as an input to evaluate this fluid force. Then we apply this fluid force as a multi-scale model to the multi-scale simulation. So that's our approach. So we have already had very promising results. We have published some paper in this during these few years, but we have to take it to more detail. We need to enhance, improve more model. So the basic model is a Shantian model. The fourth term of the sealed potential model, and then the fourth model can be written like here. So the one of benefit using lattice Boltzmann is that the sealed potential form regarding the wettability in the unresolved region. So we naturally extend this sealed potential form with the ratio of the porosity, local porosity here. Then we can take into account the solid wettability from unresolved region. So more detail can be seen here about the model. So, so this is an example case. So we think about the water invasion through the pore. So firstly, all domain, most of domain are filled by oil, then flush out by the water. So we choose the resolution 1000 by 200, which are relatively high. And then firstly, we apply very high pressure difference from the bottom to top so that we prevent some water invasion because we assume the water wet in this system. So this is a simulation result. So initially, the fine structure side is quickly filled by water, and then later on, the center, the coarse structure side is filled. So because we timely reduce the pressure difference, because of water wet, it's embedded. So next, we try to coarsen the image by 10 times from here to here. Then most of fine structures are under-resolved now. And then what we did is just we just firstly try with the post-processing, we try to coarse the simulation result by 10 times. So that's this result. So just coarsen that takes the average by 10 times the previous simulation result. So now we have a lot of irreducible oil component here. So that we need to capture. And then this is a kind of the result which we should compare using multi-scale model. So next is the multi-scale simulation. So using this coarse resolution, we try to see if we can reproduce the result in the previous slide. And then, as I said, we need to run pre-simulation as for preparing the input for the multi-scale simulation. So we firstly simulate this kind of the fine structure with high resolution and get a PCK0KR. So we use them as input for the multi-scale model. This is the result. So firstly, the size region are embedded by water first, and then the middle region embedded later. So this sequence seems to be reasonable, and then but there's a two deficits there. The one thing is that in the middle of invasion, the interface seems to be too flat here. And the second deficit is after water flushing propagates here, we don't see any digital component here as we compare here. So that's coming from the model assumption that because we don't touch anything for the intercomponent force in this under-resolved region. So this is we use a Shantian model. So to reduce the surface tension surface tension, we have to naively reduce the intercomponent force strength. Then interface becomes thicker and thicker. So it's not easy to reduce surface tension in this region. So that's the one problem. And the second here is that this seems to be, we need like a cell-to-cell component variation, but that's really hard to achieve with the diffusive interface. Yeah, because it's interface thickness is 3 or 4 box at least. Yeah. So they are the issues. So we try to address them. So first case, we try to add the additional force correction on top of the Shanchen force model. So specifically, we added this force acceleration term. It seemed to be a continuous CSF model, well-known CSF model, but we try to introduce it as a counter force on the Shanchen force. So we carefully choose this component index, and then we simulate the static droplet case. And then by tuning this kappa value, this kappa is a parameter, we can achieve the 30 times, 40 times reduced surface tension while maintaining the spurious current level and then interface thickness here. So yeah, it looks promising. And then this is the simulation result. So center is the original surface tension model. So water invasion pattern seems to be very, very flat. On the other hand, the right-hand side, because the surface tension is reduced a lot, we see a lot of fingering pattern here. So this case is that we use a random porosity distribution. So that case seems to be more realistic. Okay, so that's the first modification. And the second modification is we added a new model to handle the residual component. So to handle the capillary force in the under-resolved region, we use the input PC curve. So PC curve look like this. So from the Riberac J function similarity here, for different porosity, we can extend a different PC curve here. So with the multi-scale model, we handle the capillary force here in the leading order, but we need to capture this region to capture the residual components. So to do that, we introduce some new parameter here, PC ref and PC ref max, PC ref min, and then we see that this cross point. So this cross point indicates the residual water component amount. So by count this fluid flow separately, we try to handle this water saturation level here. Yeah. So in this way, we achieve the cell-to-cell water variation, which cannot be achieved with a diffusive interface model. So let me see. So we just compare 3 cases. First is the original, and second is the residual component model on, and third one is the residual component and the interface model is on. So we see a lot of residual component now in the side region. So that's reasonable. And then the PC curve looks almost similar. So because it's focused on the steady state, so it doesn't change so much. That's good. But if we focus on the middle stage here, so we see a lot of changes from original case. And then compared to the fully resolving case here, it seems to be reach more this fully resolving case here. So the last one is this is the last stage of the invasion. So we capture some reserve component here while we capture this reserve component in the course side. Yeah, so this, let me skip this second case. We did this. So last improvement is application extension. So some cases now we assume the homogeneous porous structure, but in some cases kind of fiber geometry, the resistivity has some directionality. So we try to handle this case. So what we did is that using the Hessian matrix, local Hessian matrix, using the local porosity, we compute the eigenvalue, eigenstate based on this matrix, and then based on that eigenvalue, eigenstate, we rotate the permeability to the proper direction, and then apply the resistivity based on this permeability. So that's our approach. So this is the demo case. So we have we assume the fiber is going through this blue region, and then red region is simply fluid, and the flow coming top to bottom. So with the scalar resistivity model, we have a much diffusive flow here because the porosity difference is small. On the other hand, the tensorial resistivity, we have a much confined velocity profile. That's because the solver automatically detects the direction, proper direction, and the resistivity applied to that direction. So flow is much confined. Yeah, so that's it. Yeah, thank you so much. Yeah. How far is what you present from the real application of the model to real application? Yeah, I think we are almost ready to apply to the real log case. So especially single scale case, actually we have already some a lot of example of the application. And then multi-scale case, yes, we have start applying a lot of. Yeah, almost the oil and gas industry application. We assume, yeah. Correct. Yeah. Some specific rock type, we have a lot of this kind of multi-scale geometry scale. Yeah.
Residual gas model, or how small can residual bubbles be? Like when you use a Shanshan, you need some quite large.
Yeah. Yeah, theoretically, it can be one voxel size. Yeah, because porosity is applied one voxel each. Different porosity has different for different box. So box size, the cell size, resolution cell size. Well, thank you very much. Yeah. All official survivors of the conference. Then there is a coffee break, and then